thanks for the introduction, and thanks for giving me the opportunity to speak here. I'll be talking about some work mostly with my student Mehmet Demirtas, Cody Long, and Mike Stillman. Also some work with John Stout, who's here, and also a little bit about some works in progress. So if the talk is about quantum gravity effects, why are we even thinking about quantum gravity? After all, for almost all scientific questions, quantum gravity decouples, and we can be safely agnostic about what the UV completion of gravity is, or even whether there is one. But some fundamental problems do depend on quantum gravity. Famously, and most importantly for present purposes, inflation, especially large field inflation. And this fits in the category of a general class of questions, the existence of certain EFTs as low energy limits of quantum gravity theories, the so-called landscape swampland dichotomy. And this situation provides us with an unprecedented opportunity to probe quantum gravity by thinking about low energy phenomena, including inflationary phenomena. Moreover, quantum gravity aside, just trying to confront these problems directly in string theory has led to new EFT models and signatures, which you can take on their own as low energy theories afterward, regardless of what their origin was. So let's just ask, for the rest of the talk, what inflationary cosmologies are possible in quantum gravity, and what can we learn from trying to answer this question in a serious way? So the plan is to tell you a little bit more about the background, describe two kinds of constructions of large field axion inflation, Axion Monodromy and Axion alignment, and in each case to tell you something about the limitations and recent advances in those areas. And then if there's time, I'll say some things about conjectures, including the weak gravity conjecture and what it has to say about large field inflation. So let's fantasize for a minute that a couple years from now we see past all the foregrounds, and behind the foregrounds, let's suppose we see evidence for primordial gravitational waves from inflation. So we see quantum gravity waves. The leading interpretation of that, as Leith famously asked and answered some years ago, would be that inflation occurred near the gut scale, which is nice, but also that the inflaton displacement is super Planckian. And that's a fascinating connection. It's an important connection. So it comes from the Leith-bound, written here. Delta phi is the displacement of the canonically normalized inflaton field in reduced Planck mass units, and R is the tensor to scalar ratio. And the reason this is an interesting connection is that in any effective quantum field theory with some cutoff lambda, if a field, in this case it'll be the inflaton field, couples with dimensionless strength g to the UV degrees of freedom, then we generically expect structure in the potential on length scales in field space of order lambda over g. Now we can't take the cutoff much bigger than m Planck in completions of field theory and gravity. And so if we see smooth potentials varying over super Planckian distances, then we must conclude that the inflaton is weakly coupled to whatever degrees of freedom UV complete gravity. So the degrees of freedom at the Planck scale have weak couplings to the low energy inflaton. In other words, the quantum gravity theory enjoys an approximate symmetry that ensures the smooth variation of the potential over multiple correlation lengths, multiple cutoff lengths. Now, this has been well understood from the level of low energy field theory for many years. Linde first proposed chaotic inflation models that enjoy just such shift symmetries. You could take p equals 2 if you want and study the chaotic inflation model with a quadratic potential, but you could pick some other p if you like. And this model has an approximate shift symmetry in which phi goes to phi plus constant that's broken only by the mass or other potential term mu. And that's nice because this theory is radiatively stable. Okay, it's protected, it's safe from loops of the light, I stress light, fields, loops of the inflaton itself and the graviton. But that's not actually the hard question. The hard question is not whether it's consistent as a low energy theory, but whether it admits a UV completion in quantum gravity. Namely, one really ought to ask, what are the effects of heavy fields, the Planck scale degrees of freedom? Those, on general grounds, one expects to give rise to something like this, a series of non-normalizable terms suppressed by some high scale, possibly m Planck, operators of various dimensions delta I, depending on the inflaton field and its derivatives, and also the curvature of spacetime, with some dimensionless Wilson coefficients. But the question is, what exactly do these terms look like? Now, the reason we have to pay attention to these terms comes in two levels. First of all, there's the eta problem, which is just the statement that terms with dimension up to about 6 have important effects for all inflationary models. There are very special circumstances where one can try to model build around it, but it's a tough game. And in general, one has to face significant corrections from Planck-suppressed operators with dimension up to about 6. That's for all inflationary models, but the super Planckian version of the eta problem is a much starker problem, and that just says that in models with super Planckian displacements, all of the operators with any delta have important effects. There's no suppression at large VEFs phi. And so one needs to somehow grapple with these terms and understand, are they present? If they're present, why? What form do they take? Now, how can we actually go about doing this? One thing you could do is you could just say, I'm going to try and use the rules of Wilsonian field theory and write down every possible Planck-suppressed operator. That's tough, especially if the theory is not weakly coupled, because how do you know which dimensions delta to write down? They're not necessarily just integers. So which operators are you going to pick, and what Wilson coefficients are you going to pick? It's not a well-defined approach. You could try it, but not a lot of progress has been made by this almost agnostic approach. Another thing you could do, and this has led to some progress, is to appeal to general consistency principles that many of us think are true about quantum gravity. Things like causality, unitarity, analyticity, also consistency requirements of black hole thermodynamics. That can tell you some things about which operators can arise, but it, again, doesn't fully clear up the picture. Another thing you could try and do, though, is study inflationary models in EFTs, low-energy EFTs, obtained from string theory. And most of this talk is about what the word obtain means. Exactly how do we obtain them, and with what confidence do we obtain them? Another thing you could do is appeal to fundamental calculations and fundamental properties of string theory, either directly on the string world sheet or holographic calculations or something like that, perhaps in flat space or ADS. In other words, auxiliary computations not directly in the cosmological solution. And finally, and most directly, you could just study compactifications of string theory that give rise to inflation or something like inflation. You would start typically by thinking about a vacuum solution, a pure geometry, and then progress to something like a flux compactification, which means a geometry decorated with data of de-branes, fluxes, quantum effects, and other sources besides. That's mostly the approach we'll be focusing on today. Now, if we want to get sharp and definite results rather than broad brush characterizations, there are sort of two most appealing approaches in my view. One is to directly construct compactifications that support large field inflation. And another, which has been very active in the community in the last few years, is to prove properties of quantum gravity symmetries, prove some no-go theorems. Now, actually, there's been a lot of activity in is conjecturing no-go theorems. And conjectures can be good. I think they're good if they lead us to A or B. If they can lead us toward a proof, or they can teach us how to sharpen our actual constructions. So there's been a productive feedback between conjectures about quantum gravity and constructions in string theory. So how do you actually do it? Well, the task in compactification is, let's say, first of all, to find a Ricci flat 6 manifold that solves the vacuum Einstein equations of critical string theory. And unfortunately, that's a hard analysis problem if you just try and solve it straight up. However, over the last decades, people have made a remarkable amount of progress using the power of special holonomy, Calabi-Yau geometry, mirror symmetry, toric geometry, all manner of special tricks that apply in special cases. But the bad news is that those methods don't entirely carry over to non-vacuum solutions. They can get you started, but once you start introducing sources, you don't really have exact special holonomy, exactly Calabi-Yau metrics, exact mirror symmetry, et cetera. And so all of the tools start to weaken when you go to the solutions that you care about, which are non-supersymmetric de Sitter or quasi-de Sitter solutions. Nevertheless, we'll try. And so in this framework, the leading approach, in my opinion, to getting large field inflation is to use an axion shift symmetry. So as a canonical example, you might think of a theory like this with a single axion and a cosine potential. F is the axion decay constant. And the point here is that the all orders continuous shift symmetry, phi goes to phi plus constant, is broken by instantons to a discrete shift symmetry. And what's nice about this theory is that axions are easy. The metric is constant. Actually, here the metric is just the number 1. I mean, if I'd used a dimensionless axion theta, the metric would have been f squared. So the metric is constant and the potential is periodic. And that nice property will persist when we study much more general theories of multiple axions. It'll still be the case that the metric is constant. It'll be a constant matrix, not a number, but still very nice compared to a general metric. And the potential will still be something like a sum of cosines. And so that's far and away easier than trying to understand a general theory of n scalars, where you have the metric on field space being an unconstrained function of all those variables, and the potential being an otherwise unspecified function. Here, for the metric, you really end up doing linear algebra only, and for the potential, you're just adding some cosines. A finite number in general of cosines. So it's not so bad. And that really is the reason that so many of us are focusing on axions, because you can make precise statements there. Now, what would you try and do? Ideally, to build an axion theory in string theory, to find an example of axion inflation, what you'd like to do is start with some discrete data. So you specify the topology of a threefold, say, and you specify the wrappings of various d-branes. You'd want to compute the metric on field space, compute the axion potential coming from instantons, and then find inflationary solutions. And I'm happy to say that we actually have made some progress. We can now carry out the first 3 steps automatically in seconds per geometry in theories with the number of axions ranging between 1 and, it turns out, 491 for reasons that I'll explain later. So that's actually pretty good in a sense. We can manufacture a lot of axion EFTs in string theory. With some caveats. Okay, so for the aficionados of axion potentials of instantons, the assumption I'm building in is I'm only studying instantons on inherited effective divisors, ignoring normal crossings. And we're writing papers trying to remove each of those provisos, but it's not ready yet. So right now, with some assumptions about which instantons contribute, we can do a real computation. And that's much of what I'll tell you about later in the talk. However, like everybody else, we're limited to weak string coupling and large volume. That's the only regime in which anybody can effectively carry out the map from discrete underlying data to a meaningful EFT with some control parameters. And it turns out that in that regime, as Banks et al. Pointed out some years ago, in that regime, single axion theories have decay constants that are very small in Planck units, and so you can't build a model of natural inflation with one axion in known compactifications of string theory. Okay, so the original proposal of Freeman-Olinto, a single cosine, has not been made to work in string theory. But there are options, 2 really good options, actually. So one is axion alignment, and this just means that instead of studying a theory of one axion, you study a theory of 2 or more axions, each of which has a sub-Planckian periodicity, but in such a way that the collective displacement of some linear combination of the axions does have a super-Planckian period. So I'll spell this all out. In this theory, the discrete shift symmetry is unbroken. The symmetry remains exact. In Axion Monodromy, in contrast, one introduces sources that do weakly break the discrete shift symmetry of the axion to nothing, but by some weak breaking parameter g, much less than 1, let's say a dimensionless parameter. In a theory like this, before introducing the source of monodromy, the field space is a circle, the axion circle. And then once you introduce the breaking parameter, the field space becomes a multi-cover of the circle, but a gently inclined one. So with each turn of the circle, each monodromy, the potential increases by an amount that's small when the parameter g is small. And if this is under control, you have a nice, smoothly increasing potential over a long range. Now, the point to note that in both of these mechanisms, you're taking small pieces and you're combining them to make something that's big. And that sort of thing can lead to artifacts in all sorts of scenarios. You can see sort of spectral signatures of the constituents of your large object. An example of this in the inflationary context is resonant contributions to the 2-point and 3-point function. So here's one example as an illustration, Axion monodromy with a linear potential. So the cosine term comes from instantons. So I'm just drawing v of phi as a function of phi, and this distance is about 11 m Planck. This model is now ruled out by tensor to scalar ratio limits, but it sort of was on the margins until recently. It's still a good illustration. In this model, with a potential like that, it turns out that there are oscillatory contributions to the 2-point function and 3-point function. And Dan and Ben and others have studied quite carefully the constraints that can be set here. In particular, this was done very nicely in the most recent Planck analysis. And there's no evidence, but it was still good to look. And there's an illustration of what I meant when I said that searching for these kinds of things in string theory, really confronting the quantum gravity limitations, presents us sometimes with effective theories that could have been written down. Yes, Lisa?
So when you say it's ruled out, you mean it's constrained to immediate
I mean it's constrained to what?
It's ruled out, I assume you mean that there's some maximal value of mu?
All I mean is that the 95% upper limit on R is a little bit below the fixed prediction of this model. In a model with a linear potential R is 0.07.
But aren't mu and lambda independent parameters?
Well, not if you try and set the normalization of the scalar perturbations, no. So you have to fix mu. So this model, okay, lambda is an absolutely independent parameter. So there's this model, in this model I can set lambda to 0 if I like. So I'm not saying that this model is ruled out because of the oscillations. It's certainly not. I can make those as small as I want. In fact, the underlying model with 0 oscillations is in very strong tension with the data. That's all I mean. And if you specify that the potential is linear, there's nothing you can do to make R much less than 0.07. You could, of course, mess with the potential.
So in the original model where they had cosine, they really needed it to be very close to the value where the potential is essentially flat.
Yes.
So you're taking some generic thing where you're assuming that you see many oscillations, and then saying, so then you're saying the source of V is coming from U.
Correct. Correct. It's the chaotic. It's the monomial potential term that's driving the tensor to scalar ratio signature. Absolutely. Yes. Yes, correct. Yeah, thank you. Yeah, these are very small in Planck units, which is why you see lots of them imprinted on the sky in this picture. Yeah. So, okay. However, these sorts of oscillatory signatures arise in all of the monodromy models, including those with smaller exponents than 1, which are not yet ruled out. So anyway, an interesting possibility, and just sort of illustrates that even if we can't directly test string theory origin of these kinds of things, it can lead us to interesting kinds of signatures to look at. Now, so let me say just a few words about how monodromy constructions work, and then I'll proceed to alignment. So a toy example of monodromy that gives the basic idea of where the mechanism comes from is to think of a D4 brane wound around a circle. And don't imagine any supersymmetry, just some four-dimensional thing wound around a circle. Then the configuration space, in simple terms at least, is the multicover of the circle. And the level that you're at on the multicover is just the winding number. That just measures how many times you've wound around. And if we wanted, we could call this a quantized charge, winding number. I'll call it a monodromy charge. That'll generalize to other settings. And the point is that the tension of this stuff, the D-brane stuff, sources curvature. It sources curvature in 4 dimensions and in 6 dimensions. Now, the sourcing of curvature in 4 dimensions is precisely the mechanism for Axion monodromy inflation. The idea was that as you rise up on the multicover of the circle, as you increase the potential, you source inflationary expansion. So the sourcing of 4D curvature, 4D de Sitter curvature, is the key to the mechanism. However, at exactly the same time, this same stuff sources curvature in the internal 6 dimensions. So let me briefly describe the generalizations before I follow up on the 6-dimensional curvature. So beyond the D4 brane toy example, Axion monodromy constructions in string theory involve some variation on the following idea. There's a physical source of monodromy. In this case, it was a wound brane. It could be a wrapped brane. And there's some sort of physical quantized charge that stores the information of which level of the multicover the system is on. There's an integer physical quantity that increments. That could be a winding. It could be a wrapping. It could be a quantized flux, an induced charge, some other thing, but it's physical. And the issue is that the back reaction of the curvature sourced by that physical monodromy charge in the internal space is not typically studied. Most papers on monodromy, that effect is omitted. It's called back reaction, but it arises at the same order of importance as the effect of the monodromy charge on the 4 dimensions, namely at the same level as the inflationary mechanism itself. So this is nothing actually new. We wrote about it in a paper 10 years ago, Ivan Alexandra and I, and we've been sort of sorting this out in every model since. Yes? Yeah, that's correct. But I think it's still true that in most papers on the subject, not yours or mine, but nor ours together especially, was this omitted. However, there's a large number of papers that talk about constructions, variations of constructions of an Axion monodromy. And all I'm trying to point out here is that this is a key issue. It's the first thing we thought about in our paper in 2008, and there are mechanisms for dealing with it.
Okay, sorry to interrupt you. That's very
Yes, I recall it, yes.
But that was actually overkill because of what we realized later, that it would actually be null.
Yeah.
So it's not that you actually have to.
True.
So it's just a bit more subtle than not even.
Right, all I'm saying is that writing down a model in which this effect is not included is almost certainly inconsistent. Writing down a model in which it's incorporated could well be consistent. One just has to do the calculation right. And I'm mentioning that only because there's an extensive literature that does things the other way, that omits these terms.
Just for clarification,
Please. Yes.
So you started off by talking about many Axion models. Then you talked about a brain rat model.
Yes.
And you lost the language of Axion. So should I keep making this as one Axion or many Axion?
One. So we had a bifurcation point. First, so I should have specified. We have two models, classes of models: alignment, which necessarily involves two or more, and monodromy, which could involve more than one, but requires only one. I'm first treating monodromy. So I'm studying a model of one axion only.
So the only interaction you're talking about is the interaction of the Axion with the background metric.
Correct. Correct. Yes. And the interaction is easy to compute in principle, because you know the stress energy of this stuff, the wrapped brain stuff or the induced charge. You can just use leading order tree level actions in string theory and compute the Einstein equations with that as a source. So let me give a concrete example. One of the reasons that this issue has been underappreciated is that in the models where we thought about it carefully, it's sort of horrendous to study because it's hard to write down a Calabi metric, et cetera. So let me take this in a toroidal example where we can see all of the ingredients and see the calculation. So there's a nice model of large field inflation in string theory that works as follows. Consider Minkowski or de Sitter times 4 torus times a T2 mod Z2 orbifold, and put some D7 brains along all the directions except the last two. Let's call those last two Z3 equals X8 plus IX9. And suppose that a stack of D7 brains supporting a gaugino condensate sits at one of the fixed point loci. Now this shading here indicates that it's a flux compactification, so there's some flux that's different here from over there. And the mechanism proposed by Ibanez, Martesano, Valenzuela is to consider an additional D7 brain that moves, that slowly moves from one side of the space to another. And as it does, it accumulates charge. The accumulation of charge is the accumulation of energy. It accumulates energy that leads to 4-dimensional accelerating expansion. So moving repeatedly around this direction of the torus, accumulating charge with each winding, is the monodromy direction. That's the multi-covered direction. Construction clear? So the game is, one is going to take a D7 brain and drag it some number of times around this cycle of the torus, each time accumulating more charge, then let it go, and it'll unwind back down. As it unwinds, it'll drive an inflationary phase. That's the proposal that they made. The point, however, is that this accumulated charge needs to be back-reacted on the internal space. You shouldn't just solve the 4D Einstein equations. You should solve the 60 components of the Einstein equations as well. So we did that, my student and I. And it turns out that the superpotential you compute on these 7 brains isn't, the actual superpotential is not the probe superpotential, but it differs by some factor, which is a power of some Jacobi theta function. Well, you should expect a theta function because I'm doing something on a torus. What you need to know about theta 1 is that at small arguments, it's linear in the argument. So you can think of this as roughly z, the separation between this brain and that brain. It's raised to a power. The power is the amount of induced charge. And that's just saying that when you've wound up a lot of times, the potential involves a very high power of the separation of this brain from that one. When you trace it through, because this q shows up in the exponent, it turns out that the moduli potential has previously unsuspected terms that are exponential in the canonical inflaton field. And so the potential, instead of being some nice monomial, also has exponentials in it. And not just plain solo exponentials, but lots of exponentials all over the place. It's way too steep. Inflation immediately ends. Okay, so the model just doesn't work. So that's an example of what I mean by, one just has to do this kind of calculation. Now, as was clear, hopefully, from the discussion with Eva, there are ways of dealing with this in some kinds of models, but one just has to try and do it. But maybe this was a little bit annoying to have to solve some, well, I didn't show you, but had to solve some PDEs to read off this result. Maybe there's a cleaner system for building axion inflation. So now let's proceed beyond monodromy to alignment. Okay. So axion alignment occurs when the effective displacement of multiple axions is much larger than the largest of the individual. periodicities. And let's see how that can happen in a toy model. So suppose I find a theory like this, where the theory of two axions, theta 1 and theta 2, that are dimensionless with this kinetic term. Now, if I imagine for a minute that this is the potential, two different cosines, cos theta 1 and cos theta 2, well, the cosines introduce a discrete identification in the field space, and they break up the field space into domains. A fundamental domain for that identification is very simple here. It's between minus pi and pi in theta 1, and between minus pi and pi in theta 2. So it's a square. And the diameter of that square is 2 pi root 2 f. So the axion field range is pi root 2 f, which is, in general, not big, because we can't usually make the constant f big in quantum gravity theories. Now, you might say, though, what if, instead, the potential was a little different? It was cos theta 1 plus theta 2. Now, let's ask where the identifications arise in this case. Now, if I take theta 1 to be minus pi, I can take theta 2 all the way up to 2 pi before I reach the first hill. So the fundamental domain looks like that. And the diameter is now root 5 instead of root 2. And I can keep playing this game. I can keep adding larger numbers. And eventually, I get a large diameter that scales like the integer k that I can put in here. Now, you should be skeptical of this. And you should say, well, wait a minute. If you take that integer to be arbitrarily big, that's an arbitrarily good global symmetry. Isn't there some problem with really good global symmetries in quantum gravity? Yeah, we would certainly be assuming the answer if I just wrote down an effective theory with some nice charges that I liked and said, I've solved the problem of large field inflation in quantum gravity. This is the Kim-Nilles-Peloso mechanism, but they knew what the problem was, but they constructed it in low energy field theory. The task is to determine, can this ever happen in string theory? Can we find aligned inflation in string theory? Okay, and I emphasize that the only thing you need to know is the axion charges, namely the integers appearing inside these cosines in front of the thetas. You have to know what axion charges do the various instantons carry. Well, we can do that, actually. And now this comes to the point about automatically enumerating theories. So as the last main topic, let me now describe how we've gone about trying to enumerate axion theories arising in string compactifications. We do it by enumerating Calabi-Yau threefolds. And let me just remind you, terminology, a polytope, you probably know, is just the n-dimensional generalization of a polygon or polyhedron. And it is a fact that many Calabi-Yau threefolds, possibly most, although no one can prove it, can be obtained in some process from four-dimensional reflexive polytopes. A polytope is reflexive if it's a lattice polytope, and the only lattice point that's interior is the origin, and its dual is also has that same property.
So you're not assuming the regular?
No, I'm not assuming regular. Definitely not regular in general. So there are going to be, tons and tons of these things. Yeah, just reflexive, just that it and its polar dual only have the origin as an interior lattice point, have lots of other lattice points on the boundary. Now, these polytopes have been classified. You can do it yourself in two-dimensional polytopes. There are 16 of them. Kreutzer and Skark did it in 4 dimensions, and there are 473 million of them. And each of these gives rise to at least one and possibly a huge number of Calabi-Yau threefolds. How do they give rise to those threefolds? Well, I'll go through a little bit of it. The process of computing the data of the effective theory in these cases requires only that we triangulate the polytopes. So to triangulate a polytope just means to break it up into simplices, into triangles, tetrahedra, etc. So there are, for example, no squares left. So for example, there's a triangulation of a square, but there's another one like that. Now when you've got a lattice polytope with lots of points, there's a huge number of different ways you can triangulate, because for example, for each square, you can pick the one triangulation or the other. Okay, so there's a combinatorially large challenge there. On the other hand, okay, so I know this is a meeting on analytic methods, but analysis is just way too hard for trying to find string compactifications. You don't want to try and nobody can actually solve the Monge-Ampère equation to find a Ricci-flat 6-manifold directly. That's just too hard a PDE for present skills. Now, it would be a lot easier to find a polynomial equation whose solutions guarantee the existence by Yau's theorem of a Ricci-flat metric. Namely, they tell you you would be able to solve Monge-Ampère equation. But that's also too hard for me. However, you can reduce the algebraic geometry problem from analysis to polynomials to pure combinatorics, to counting lattice points. And that's easy because you can then put it on a computer and get it done. And so that's what we've been doing. So the program works as follows, the intellectual program. I'll say something about the computer program momentarily. So to specify the geometry of the Axion fundamental domain, these polygons I was showing you before, these rather distended polygons, first you compute the metric on the Axion field space. So remember, in a theory of n axions, this metric is just a constant n by n matrix. So we want to compute that matrix, and we want to understand what are the instanton contributions. So we want to know, do we see cos theta 1 or cos 2 theta 1 plus theta 2, or what? So what are the axion charges of instantons? And the way you do that is, OK, you pick a polytope from Kreutzer and Skark's database. You triangulate it to reach what's called a toric variety. You can then find a hypersurface in there that's a Calabi-Yau threefold. If you're a little bit enterprising, you can compute the intersection numbers of that threefold. And it turns out that that tells you pretty much everything you need to know about the classical theory of string theory compactified on that Calabi-Yau threefold. Not the quantum theory. To get the quantum theory, you have to go a little further. You next enumerate what are called rigid divisors of X. These are just hypersurfaces, four-dimensional surfaces in the threefold that are not distortable. They're just fixed in place. You can't twist them or stretch them at all. And at this point, you actually know a lot of things about the 4D Lagrangian. Not perturbative corrections, but you know certain non-perturbative ones, and you know all the classical data. So now you can compute the field range. So here's the arena. This is Kreutzer and Skark's data plotted in an H11 and with axes H11 and H21. These are Hodge numbers. So this is the number of 3 cycles. This is the number of 4 cycles inside the space. From 1 up to here, 491. That's the biggest one. That's where that number came from. In their list, there's just a maximum. And the way to read this is easy is down here, hard is up there. The reason is H11 also corresponds to the number of lattice points in the polytope that you're trying to triangulate. The more points you have, the more different triangulations there are, and the more complicated it is to figure out which ones you want and to get effective theories from them. So people have been thinking about this for some time. There are many systematic studies for H11 up to about 6. So that's this really thin green band here. And there's just a few studies with H11 up to 20, but of very limited things. And took us a while, took us a couple years actually, but I'm happy to say that now we've got access to the whole thing in seconds per geometry. And let me just describe what was required in accomplishing that. People were limited previously because the algorithms for computing triangulations were too slow when H11 was bigger than about 5. So we fixed that. Then it was limiting that computing the intersection numbers was too slow for large H11, so we fixed that. And then it turned out one needed to come up with new ways of computing the topology of 4 cycles inside this 6 manifold. And so we figured out an algorithm for that also. And then we just put them all together. My student Demertas assembled all of this as a sort of a package, not public yet. Eventually it will be. And now you can just press go, and you can find whichever geometries you want. So right now we've only explored 2 million. But this is just the first reporting of any results from our analysis. We just got our machines working. And there's much more to come. Yes?
It's kind of clear that if those other guys could do more, you'd end up in much higher values.
No, actually, than 491. Yeah. That's a complete classification. When Kreutzer and Skark said there are 473, 800, 776, that's the end. There aren't any other polytopes with larger H11 that are reflexive. Now, can there be Calabi-Yau threefolds with larger H11? No one can prove that there aren't, but it's suspected that there aren't any, actually. Waddy-Taylor is making a series of works that push in the direction of connecting these things to actually known classifications of elliptic fibrations where you do get a provable hard limit. If he can complete that link, then you'll know that this is actually the end of it. Now, what you don't know is where most of the geometries are. The reason is some of these points are individual polytopes that have, say, 10 to the 20 triangulations. In some cases, those are all distinct threefolds. And so we're just beginning to understand, we and others, beginning to understand where most of the Calabi-Yau hypersurface in toric variety threefolds are. Then what remains is a whole other realm. So that remains to be figured out. However, this is a really fruitful realm for the reason of reducing things to combinatorics that I described. You can actually just go through this whole ensemble, and in principle, I think it would take us about a year, but I think we could get one triangulation for every single one of these 473 million. And then you start to get a picture of what phenomena are possible. OK, so what do we find? Well, I mentioned that we're limited to the regime of weak coupling and large volume. So let's talk about the large volume. For the alpha prime expansion to make sense, we can't have too many really small cycles. So we impose the requirement that every curve, every holomorphic curve, 2-cycle, has volume at least alpha prime. I'll call it 1. I'll work in units of alpha prime. When you do that, it turns out that the whole space has to be gigantic. So what you see here is the volume of the threefold, so that's a 6 volume, log 10 of it versus H11, only up to 100. And you see, it's already up at like 10 to the 10. So these are pretty big spaces. Now you can take a 6th root if you want to find the radius, but it's still sort of big in string units.
Isn't the relevant quantity the collision mass? I mean, again, having a crush of thinking of a
Yeah.
the volume can be huge, but the gap is still large.
Yeah, that's right. This is not a crisis. This is just the prelude to an interesting thing. Yeah. Right. So from this, what do you read? You're like, oh, the things are big. Whatever. No problem. However, it also follows that the 4 cycles are big because the 6 manifold is big. And so now let's see what that means. So suppose I take some basis of 4 cycles. It has H11 elements. I'm going to sort them from smallest to largest. Each of them is a 4 cycle. They all have volumes. Call the smallest volume tau 1. Call the biggest one tau last. Well, you can compute the volume of the last one in our example. So here in our ensemble of a couple million things, here's the log 10 of tau last. And what you see is also the 4 cycles are pretty big, 10 to the 6 or something like that. The reason that that's interesting is instantons wrapping 4 cycles are the only thing that can give potentials to 4-form axions. So the axions that I was implicitly talking about so far come from a reduction of the Ramon-Ramon 4 form, C4. The only way that can receive a potential, due to the non-renormalization theorem, is if there's an instanton wrapping a 4 cycle. If every 4 cycle has volume of order 200, then the action of every instanton is at least of order, actually, 2 pi times 200, and you can neglect them all. The axions are massless. It's not, I haven't shown you here that every cycle is large. I've only shown you that the biggest one in a basis is always big. What that means is that at least one of the axions, the axion who receives its potential only from the last and biggest 4 cycle, is ultralight. It has a mass less than e to the minus 2 pi times this number tau last. Right? I mean, look, if I had n axions and only n minus 1 instantons, one of the axions is massless. If I have n minus 1 regular instantons and one really suppressed instanton, one of the axions is really light. That's all I'm showing you here. How light? Well, e to the minus 2 pi tau last. Well, let's work it out in useful units. This line is 10 to the minus 33 electron volts. So every blue dot above the red line is a Calabi-Yau geometry with the property that at least one of its axions is lighter than Hubble today. So an ultralight axion. Now, these are not automatically ruled out. They would certainly be ruled out if you had produced a lot of them. Then you'd have ineffective kind of constraints. But we don't know that these things are necessarily produced. So I don't think this model is yet ruled out, but it's pretty interesting. Pardon me? Present day Hubble. 10 to the minus 33 eV. Yeah, these are really light. Right, these are, when people say ultralight axions and they mean 10 to the minus 22, no, these are a lot lighter than that, actually. These are ultralight axions. We can get some in the 10 to the minus 22 range, certainly. But all of this argument is saying is that the vast majority of geometries in our ensemble have really light axions. Yes, Sean?
Does the same argument say there's also a whole bunch of slightly heavier axions?
Yeah, absolutely. Yeah, so I could repeat this slide with tau h11 minus 1, and it would shift down an infinitesimal amount. We didn't yet quantify, how many have 7 ultralight, how many have whatever, but we're working on that. Yes, we just picked this because somehow you could point to it and be sure that you had at least one. But yes.
Do they come with the matter of 1 over f or 1 over n?
1 over f. These have some decay constants f. Yeah, oh, the decay, very good. Now let's go to the decay constants. So r here is the radius, namely half the diameter of the axion fundamental domain. Now it's the quantity that I wanted to be big for large field inflation. This is log 10 in Planck mass units. So, this line is reduced Planck mass. And you see that these things are all really small. Every single one of our geometries that we can trust has a small decay, has small decay constants and small field ranges. No alignment yet. We can't find large alignment yet. For people who care, I can explain afterward. There's a pretty complicated story about the proviso I just said when I said every one of the geometries that we can trust Those are the ones I'm showing you here. There are some geometries where we're not sure that the alpha prime expansion is under control. And in those, actually, we see ranges like 10 M Planck, 30 M Planck. But I can't present those to you now because I don't think that we can count on them. Yes?
The axions here interact with each other, or you just know?
Yeah, the leading interaction comes from there's a kinetic matrix. Once you've diagonalized that, the leading interaction comes just from the cosines. So there's some cosine. The potential looks like some sum I is equal to 1 to h11 of lambda I to the fourth cos qij theta j. At least that's the first h11 terms. They look like that. And so at the quadratic level, there's some Hessian matrix coming from these q's.
And there's no pattern necessarily to this.
It's a good question. We were strongly motivated by prior work. Yeah, OK, thank you. Let me comment actually on part of the strategy underlying this. Why am I looking at large h11? Well, first of all, because that's where most of the geometries are. But also because at large h11, you can try to expand in 1 over h11 and build a random matrix model. So you might try, we certainly tried, to describe Q and also the kinetic matrix and also the Hessian as random matrices. And what I have to report so far is that it was disappointingly difficult in the sense that there's more structure in the data than I would have naively expected. And you know how it works in random matrix theory. If you go to bigger and bigger matrices with relatively clean inputs, you get beautiful central limit type behavior. If your inputs are a little bit polluted or correlated, you have to go to quite big sizes. Right now, we've only fully explored up to about 100 by 100 matrices, and random matrix behavior is not effectively setting in. I'm hopeful, but, and I really think this is one of the ways of getting analytic understanding of what kind of effective theories come out, but I can't quote the results. Please.
If you have these interactions, do you have interactions among axions with different acids?
Yeah, sure. I mean, you mean quartic interactions? Yeah.
Yeah, just like there's no constraint that they have to be similar in mass or anything like that.
No. I mean, the only constraint would be constraints that you can derive from it coming from a sum of cosines like this. And the sum of cosines comes from the fact that we insisted on a large volume so that all the weakly coupled instanton expansion works. So then you get this, and the only question then, I should have written here also, the kinetic term is some kij d theta I d theta j, and the data of the theory is two matrices, right? The kinetic matrix and the charge matrix. And our task is to go from topological data to those matrices and come up with outputs. Right now, we haven't boiled things down enough that I can with confidence tell you what these ensembles are. You might have said this should be some, perhaps, Wishart ensemble, some positive definite ensemble, and you might have had an idea of what this would be. I had lots of ideas about what those would be, and my guesses are all wrong so far. So I'm gonna wait until we've sort of sorted through the data a little further. OK, so well, no time to talk about weak gravity. Let me just mention the bottom line about weak gravity is that the weak gravity conjecture does not rule out axion alignment because of something called the superextremal loophole, which just means that if the weak gravity conjecture, in short, for those who've seen it before, this may make sense. The weak gravity conjecture tells you that every possible instanton charge has an associated instanton that's relatively important. And that's this low level of importance sketched here. What you could ask is, well, can I make the instantons that do a special job for me even more important? Then I fulfill the conjecture automatically, and I still get to construct a theory that has some interesting mechanism of alignment. So here, these are the instantons supporting alignment, and these are all the other ones mandated upon you by the weak gravity conjecture if you believe it's true. But that's a story for another time. Let me say there's just one other thing that's preventing us from really answering from being able to really say whether the theory that I'm writing down for you is correct. And that's that all of the instantons I was talking about were superpotential instantons. That is to say, they come from Euclidean branes wrapping holomorphic force cycles. And we have to go into some really undiscovered realm to grapple with non-holomorphic ones, where you can't use any of these nice tools of special geometry, Kähler geometry, even complex geometry at all, and you have to do actual analysis. And that's where we're stuck right now. So let me conclude. We tried to characterize quantum gravity constraints on axion shift symmetries and axion theories. I told you about two leading approaches, monodromy and alignment. Axion monodromy inflation constructions are limited by the back reaction of monodromy charge, just from solving the 10-dimensional Einstein equations. But that can sometimes be ameliorated. It just needs to be included. Axion alignment doesn't have such a problem, but it requires specific characteristics of the charge matrix of axion charges carried by instantons. And so to answer whether axion alignment is even possible in quantum gravity, we just set out to find axion theories, explicit axion theories with quantized charges, integer matrices Q in string theory. We did that. We found some millions of them. And so far, no high degree of alignment. But I also can't yet rule it out. I think the machines that we've built up for this are quite powerful, and I suspect that in a few years we'll have a great deal more information about it. So far, in summary, we found no super Planckian ranges, but we did find ultralight axions. And it's possible that some of these ideas could be limited by conjectures like the weak gravity conjecture, but so far to me it has seemed most fruitful to push on this by attempting to enumerate rather than by trying to guess what the answer will be. Thanks.